A doubling will make the rate go up by 4, B tripling will make the rate go up by 3, so the total goes up by a factor of 12 by doing those two alterations. So A is second order, so doubling A will have a larger effect than cutting B in half. And so you'll end up increasing the rate by 4 and then decreasing it by 2, so the rate will go up by 2 as a net. Rate determining step is your slowest step, and that's going to be the one with the highest activation energy. So the step from C to E is the one with the largest increase in activation energy, actually in both directions. That'll be the rate determining step. X is 1 because you see that increasing the concentration of A by 3 increases the rate by 3 as well. And so therefore the exponent attached to A must be 1, usually 0, 1, or 2. So the slow step in here is the rate determining step. It's going to determine your kinetics based on what the reactants are. So your rate is going to be equal to K times A times B, as increasing A or B will increase the collisions between them. The slope of a first order reaction for natural log of concentration versus time is linear. The slope will be the rate constant. Usually it's negative, so A here must be a product instead of a reactant. So you just have to simply add things up. The e's will cancel as they are intermediates, and you'll end up with 2x plus y makes 2c plus b. So the only thing missing from that equation is the b. Reaction order is just what the sum of the exponents are. So A is second order, B is first order, and then the overall reaction order is the sum of those two, so it would be third order overall. So the rate law there has a 1 on the NO, indicating that it's first order, and so therefore a plot of natural log of the concentration of NO will be linear like that, and the slope will be the rate constant and negative. So the units have to cancel to give you molarity per time for rate, so molarity per second, let's say. So then you have to cancel one of the molarities by doing a molarity to the -1, and then time to the -1 for the units of K to cancel out the two concentrations, one of the two concentrations. So again, we see natural log of concentration versus time. That's indicative that we have a first order reaction, so x here would be 1. That would be our exponent attached to A. This is derived from the Arrhenius equation. So when you get a slope of negative activation energy over R, you've plotted natural log of the rate constant K versus 1 over temperature in kelvins, and that will give you that slope. So again, the rate determining step is your slowest step. There's two steps here, a fast one and then a slow one. The second step is your rate determining step by virtue of having the largest activation energy. Your transition states can also be called activated complexes, and that's when you're in between the point where you're breaking the bonds and forming new bonds. So at B, D, and F at those high points are where those would be. An intermediate, on the other hand, is consumed after being produced in the middle of the reaction. So C and E would be the points where you're intermediates, where you've made something new that's later going to get used up when you get to your products at G, but you didn't have at the beginning at A. So again, here we see the intermediate is XY, it gets formed in the middle of the reaction, and then later in the second step it gets used to make the final products. So that would be your intermediate, the XY. So from your elementary steps, the slow step, the rate determining step, is the first one. So your rate's going to be equal to rate equals K times X times Y, because increasing X or Y will increase the collisions in that rate determining step. Mechanism 1 is correct here. There are two things. One, it has two steps, just like the activation energy, or the reaction profile. And then secondly, the first step is slower and has a higher activation energy for both. As activation energy goes up, you end up with a larger exponent, but it's negative, and that's going to make the rate constant become smaller. We can counteract that with temperature, which is the opposite effect. So the slope of this particular line is how you find activation energy. This is again derived from the Arrhenius plot you can see in a previous flashcard. So if you plot natural log of rate constant versus 1 over temperature, slope is negative EA over R. So A needs to bond to C in order for this reaction to occur, and it's currently has B in between. So that collision will not lead to a reaction. It has the incorrect orientation in order for the reaction to occur. So reaction 1 is a typical reaction profile of a single step. Reaction 2 has 2 steps, but it's faster with lower activation energies. So that would indicate that reaction 2 is being catalyzed. So here we have a second order reaction, so plotting 1 divided by concentration of A versus time should give you a straight line. The slope of that line should be a positive rate constant, so here we must be looking at a product.